Question 1.1 asks us to choose the molecule with hydrogen bonds. A hydrogen bond is a strong intermolecular force of attraction between a slightly positively charged hydrogen atom that is covalently bonded to a very electronegative atom, such as nitrogen, oxygen, or fluorine, in one molecule, and a slightly negatively charged nitrogen, oxygen, or fluorine atom of a nearby molecule. Each of the given compounds contains oxygen, which is highly electronegative, but we need to expand their structures slightly or draw their full structural formulas to see if the oxygens are bonded to hydrogen. This compound contains an ester group. This compound is an alcohol with a hydroxyl group on the last carbon atom. This is a ketone with a carbonyl functional group. And this is an aldehyde because at the end of the molecule there is a carbon double bonded to an oxygen and single bonded to a hydrogen. In each compound, the electronegative oxygen pulls electron density towards itself and becomes partially negatively charged. The atom to which the oxygen is bonded is less electronegative and becomes slightly positively charged. The slight positive charge is on a carbon atom in the ester, ketone, and aldehyde. The delta positive carbon is attracted to a delta negative oxygen on an adjacent molecule. These forces of attraction between polar molecules are called dipole-dipole interactions. They are relatively weak. Notice, however, that in the alcohol, a highly electronegative oxygen atom is bonded directly to a delta positive hydrogen atom. The partial charges which form result in a strong hydrogen bond between the delta positive hydrogen on one molecule and the delta negative oxygen on a molecule nearby. Hydrogen bonds are found in the alcohol, and so the answer is C. Question 1.2. We are asked to select the general formula of carboxylic acids. A carboxylic acid has a carboxyl functional group, and the carbon of the carboxyl group is bonded to an R group. If the R group is a methyl group, for example, we now have two carbons in the chain, and so this carboxylic acid is called ethanoic acid, which we find in vinegar. If the R group is an ethyl group, then there are three carbons in the carboxylic acid, and so it is called propanoic acid. We can use these two examples of carboxylic acids to deduce the general formula. In ethanoic acid, there are two carbons, 4 hydrogens, and 2 oxygens, so its molecular formula is C2H4O2. In propanoic acid, there are 3 carbons, 6 hydrogens, and 2 oxygens, so its molecular formula is C3H6O2. Notice that if we simplify these two formulas, we get the same general formula, CnH2nO2, where N is the number of carbon atoms. This is the general formula of carboxylic acids. So the answer is C. We are asked to give the IUPAC names of the two compounds. Here we have called the unknown compounds X and Y. Let's have a look at reaction 1. The reactant molecule is an alcohol. In the paper we were given a condensed formula, but here we have expanded it a bit, which helps us identify it as an alcohol, since we can now see that it has a hydroxyl functional group. There are 4 carbons in the chain, and so the root name is bute, and we can number the chain starting on the end closest to the functional group. There are no double or triple bonds in the chain, and so it is a saturated compound, and the name becomes butane. Since the hydroxy group is on carbon number 2, the suffix is 2-ol, so this alcohol is butane 2-ol. We are told the alcohol is treated with concentrated sulfuric acid. We need to know that concentrated sulfuric acid is a dehydrating acid, and the reaction is therefore a dehydration reaction. This means that a water molecule is removed from the compound. But where did the water come from? It came from the hydroxyl group and an adjacent hydrogen. When an alcohol is dehydrated, it forms an alkene, which has a double bond between the two carbon atoms which lost the water molecule. Alkenes are unsaturated. This alkene has 4 carbons, so the root name is bute. We number this alkene from the end closest to the double bond, and since the alkene is symmetrical, we can number it like this or like this. The suffix is -ene, indicating that the compound contains a carbon-carbon double bond. We need to indicate where in the chain the double bond is. The double bond is between carbons 2 and 3, and so in the name we write the position of the double bond using the lower number of the 2 carbons involved. So this alkene is bute-2-ene. Bute-2-ene is then used in reaction 2, and we are told it is a hydrogenation reaction. And so one of the reactants is hydrogen gas. Alkenes can undergo addition reactions, where the double bond opens up and 2 new groups or atoms add on to the 2 carbon atoms where the double bond was. In the case of hydrogenation, one hydrogen atom adds onto one of the carbon atoms, and the other hydrogen atom onto the other carbon atom. Since each carbon atom in the product has 4 single bonds, the compound is saturated. Saturated hydrocarbons are called alkanes. The IUPAC name of a 4-carbon straight-chain alkane is butane. Finally, the IUPAC names are bute-2-ene and butane, which is answer B. Question 1.4. We are given the reaction X plus Y reacts to form Z in an equilibrium, and we need to use the diagram to figure out the value for the heat of reaction as well as the activation energies for the forward and reverse reactions. On a potential energy diagram, we have potential energy on the y-axis and the course or progress of reaction on the x-axis. The first horizontal portion of the diagram is the potential energy of the reactants, which are X plus Y. This energy we can write as H reactants. The second horizontal portion is the potential energy of the product, Z, whose energy is H product. Notice that the energy of the reactants is higher than that of the product. And the difference between these two values is delta H, the heat of reaction or enthalpy of reaction, which is shown by the red arrow on the graph. Since the energy of the product is less than that of the reactants, delta H is negative, and the forward reaction is exothermic or energy releasing. So the answer cannot be C, which has a positive heat of reaction. Then the energy that needs to be absorbed by the reactants to reach a transition state is the activation energy of the forward reaction. Activation energy is the minimum amount of energy required for colliding molecules to undergo a reaction. And if we consider the reverse reaction, which is Z decomposing to form X and Y, we would need to read the diagram backwards. The activation energy needed by Z to form X and Y is given by the pink arrow. This is the activation energy of the reverse reaction. Comparing the sizes of the arrows for the forward and reverse reactions, we can see that the activation energy of the reverse reaction is larger than the activation energy of the forward reaction. Only in answer D is there a negative heat of reaction and an activation energy of the reverse reaction larger than that of the forward reaction. So the answer is D. Question 1.5. Here we need to compare the concentrations of the species at equilibrium. This is the equilibrium reaction. To determine the relative concentrations of the species at equilibrium, we can use an ICE table, where I is the initial moles of each species, C the changed moles, that is, the moles of each species either used up in the reactants or produced in the product. And E is the number of moles present at equilibrium. We are told that the moles of the two reactants are equal at the start of the reaction, and so let's call their values A, since we do not have their actual mole values. At the beginning of the reaction, there is no hydrogen iodide, and so its mole value is 0. Then the line on the table for the changed moles always has the values in the same ratio as the stoichiometric coefficients in the balanced equation. In other words, the changed moles depend on the molar ratio. So since 1 mole of hydrogen reacts with 1 mole of iodine to produce 2 moles of hydrogen iodide, if we then say that X moles of hydrogen reacted, and we are calling it X because we don't know the value, then the same number of moles of iodine must also react according to the balanced equation. And double the moles of the product must form, that is, 2X. Then, to work out the moles of each reactant present at equilibrium, we must take the moles we started with and subtract the moles which were used up in the reaction. And we get A minus X moles for each reactant left at equilibrium. And for the product, we need to find the sum of the initial moles and the moles that were produced. And we get 2X moles. We can see that no matter what the actual values are, that the equilibrium moles of the two reactants are always equal. But the answer options are in terms of concentration and not moles. And we know this because the answers are written in square brackets. Since concentration is equal to moles divided by volume, we can write the concentrations of the two reactants like this. But all the gases are in the same volume, the same vessel. Therefore, the concentration of hydrogen gas and iodine gas must be equal at equilibrium. And so the answer is A. Question 1.6. The question asks us to choose the answer which increases the yield of sulfur trioxide. We are given this reaction where sulfur dioxide reacts with oxygen reversibly to form sulfur trioxide. Le Chatelier's principle governs the position of an equilibrium and how much yield of product forms in a reversible reaction. It says that when a stress or a change is applied to a system at equilibrium, the equilibrium will shift to relieve the stress. The factors which affect the position of an equilibrium are the concentration of solutions, but we do not have any solutions in this equation, temperature, and the pressure or volume of gases. Answer option A says oxygen gas is added. Notice that all species in this equilibrium are gases, and that we have a molar ratio of 3 in the reactants and 2 in the products. Increasing the pressure of a system at equilibrium favors the side of the reaction with fewer moles of gas. Adding oxygen gas would increase the pressure of oxygen and increase the moles of reactants. Therefore, the equilibrium would shift to the right to decrease the moles of gas. And as a result, more sulfur trioxide gas is produced. In other words, the yield of sulfur trioxide increases. We can see that the answer must be A, but let's check the other 3 answer options. Answer B mentions adding a catalyst. A catalyst is a substance which speeds up a reaction by lowering the activation energy required for a reaction to occur. In the case of a reversible reaction, both the forward and reverse reactions are faster when a catalyst is present. A catalyst is not used up but remains unchanged at the end of the reaction. Although a catalyst speeds up a reaction, it does not affect the equilibrium or the yield of product. Answer B is incorrect. Then answer C mentions increasing temperature. We are also given the heat of reaction, which is negative, and this tells us that the forward reaction is exothermic, meaning energy releasing. Therefore, the reverse reaction must be endothermic, meaning energy absorbing. Increasing the temperature of a reaction at equilibrium favors the endothermic or energy absorbing reaction. So in this case, the reverse reaction is favored since it is endothermic. Increasing the temperature will cause the equilibrium to shift towards the left, towards the reactant side. This will result in the yield of sulfur trioxide decreasing. We have confirmed that answer C is incorrect. Finally, answer D mentions increasing the volume of the container. Increasing the volume of a gaseous equilibrium has the effect of decreasing the pressure. This will shift the equilibrium towards the side with more moles of gas in order to increase the pressure again. And in this case, increasing the volume, the equilibrium will shift to the left. The result is that the yield of sulfur trioxide will decrease. We have confirmed that answer D is incorrect. Finally, the answer is A. Question 1.7. In this question, we are given the ionization constants for butanoic acid and ethanoic acid at room temperature, and we are told the two acids have the same concentration. We have to identify which statements are true. This is butanoic acid. It has 4 carbons in the chain, with a carboxyl group or a carboxylic acid group at the end. And this is ethanoic acid. It has 2 carbons in the chain, with a carboxyl group at the end. Ka is the ionization constant or acid dissociation constant. The magnitude or size of Ka indicates the strength of an acid, and the strength refers to the degree to which the acid ionizes in water. Strong acids ionize or dissociate fully in solution, and so we show a full-headed arrow. Weak acids ionize only partially into ions in water, and we show this using an equilibrium arrow, since some of the products recombine to reform the reactants. The Ka expression is the concentration of the products divided by the concentration of the weak acid. We do not include water in the Ka expression. We can see that both of the Ka values are small since the exponents are negative. So both these acids are weak acids. This is the equation for the ionization or dissociation of butanoic acid, and this is its acid dissociation constant expression. Then here is the equation for the ionization of ethanoic acid with its Ka expression. Since butanoic acid has a smaller Ka value than ethanoic acid, this tells us that butanoic acid dissociates or ionizes to a small degree, and so the concentrations of its ions in the products are low. Since ethanoic acid has a larger Ka value, this tells us that ethanoic acid dissociates to a larger degree than butanoic acid, and so the concentrations of the ion products are higher. To summarize, the smaller the Ka value, the weaker the acid, and the larger the value, the stronger is the acid. So we can conclude that although both acids are considered weak, butanoic acid is weaker and has a lower concentration of hydronium ions. So the answer is B. Question 1.8. In this question, we need to find out which reaction results in the highest pH. We are given these acids and these bases. We know that when an acid and a base react, a salt and water are produced. Let's write the equations for each reaction. When nitric acid and potassium hydroxide react, the products are potassium nitrate and water. We can see the potassium ion from the base and the nitrate ion from the acid form the salt potassium nitrate, and the hydrogen from the acid and the hydroxide from the base form water. In a similar way, when hydrochloric acid and sodium hydroxide react, sodium chloride and water form. When ethanoic acid and sodium hydroxide react, sodium ethanoate and water form. But the last reaction is slightly different. Ammonia is a gas, and when it comes into contact with the water in the hydrochloric acid solution, the ammonia reacts with the water to form ammonium hydroxide, which is a weak base. Weak bases dissociate partially into their ions, and in this case ammonium ions and hydroxide ions. So we could write the equation like this. Hydrochloric acid reacts with the base ammonium hydroxide to form the salt ammonium chloride and water. All of these equations are balanced with a 1:1 mole ratio of acid to base. We know that strong acids and strong bases dissociate fully or completely in solution. In red, we have the general equations for this. Because the dissociation is complete, a strong acid produces a high concentration of hydrogen ions in water, which can react with water to form hydronium ions. These acids shown in yellow, namely nitric acid and hydrochloric acid, are strong and produce a high concentration of hydrogen ions in solution. Since strong bases dissociate fully, they produce a high concentration of hydroxide ions in solution. The bases in yellow are strong bases, namely potassium hydroxide and sodium hydroxide, and they produce a high concentration of hydroxide ions. Weak acids and weak bases dissociate only partially, forming an equilibrium with their ions. Weak acids therefore produce a low concentration of hydrogen ions and, in turn, a low concentration of hydronium ions. Ethanoic acid is a weak acid and produces a low concentration of hydrogen ions in solution. Weak bases dissociate partially and produce a low concentration of hydroxide ions. Since ammonium hydroxide is a weak base, it produces a low concentration of hydroxide ions. Now that we know the equations for each acid-base titration and the relative concentrations of hydrogen ions and hydroxide ions, we can start to deduce the final pH of the reaction at equivalence point. Equivalence point is the point in a titration at which the acid and base have both been used up and neither is in excess. This happens in each of these equations when the moles of each acid and base are the same according to the 1:1 mole ratio. A strong acid and a strong base with a high concentration of hydrogen ions and a high concentration of hydroxide ions will produce a neutral pH at equivalence point. A weak acid and a strong base will result in a slightly basic pH at equivalence point, so the pH will be above 7. And a strong acid and a weak base result in a slightly acidic solution at equivalence point, and so the pH is below 7. So the pair which gives the highest pH is ethanoic acid and sodium hydroxide, which is answer D. Question 1.9. Here we are given a galvanic cell and we need to deduce the material the cathode is made from, as well as the direction in which the current flows. A galvanic cell, also called a voltaic cell, is an electrochemical cell in which a spontaneous redox reaction occurs, generating electrical energy. In other words, current is produced in the wire. We have two half cells, one with a cadmium electrode and cadmium 2+ ions in solution, and the other with a silver electrode immersed in a solution of silver 1+ ions. We can use the data sheets to work out the half cell in which oxidation occurs and the half cell in which reduction occurs. On the table of standard reduction potentials, we can find the half reaction for the reduction of cadmium ions to cadmium and the half reaction for the reduction of silver ions to silver. We can also find their corresponding electrode potentials in volts. If a value is less positive or more negative, this tells us the element is more easily oxidized. If a value is more positive or less negative, the element is more easily reduced. So cadmium will be oxidized and silver will be reduced. Now, oxidation always occurs at the anode, so the cadmium electrode is the anode. And reduction always occurs at the cathode, so the silver electrode is the cathode. During oxidation, each cadmium atom loses 2 electrons into the wire, which travel up the wire to the other electrode. The anode is the negative electrode, since electrons are released from atoms there and are freed to go up the wire. Since cadmium atoms lose 2 electrons, they are converted to cadmium 2+ ions, which go into solution. Over time, the mass of the cadmium electrode will decrease as ions are lost into the solution. This is the oxidation half reaction which occurs. The other electrode, the cathode, is the positive electrode, which receives electrons from the wire. Positively charged silver ions in solution each gain an electron and are reduced to silver metal atoms, which plate onto or deposit onto the cathode. So the mass of the cathode increases over time. This is the half reaction for the reduction process. From the two half reactions, we could write this overall or net reaction. Finally, we can see that the cathode is made from silver, and the electrons flow from the cadmium electrode to the silver electrode through the wire. So the answer is B. Question 1.10. In this question, we are given an electrolytic cell and we are told that we want to plate the iron rod with nickel. An electrolytic cell is an electrochemical cell in which a power source drives a non-spontaneous redox reaction. We are given the cell symbol in the question paper. The long side represents the positive terminal of the cell and the short side the negative terminal. Electrons are considered to flow out the negative terminal, making the electrode attached to it negatively charged. The other electrode is positively charged. The only ions in solution that we need to consider are nickel ions. Nickel ions commonly have a 2+ charge. The nickel ions are attracted to the negative electrode where they each gain 2 electrons. Nickel ions are reduced to nickel metal. The nickel metal atoms which form plate onto or deposit onto the electrode. So this electrode must be the iron electrode, as we wanted to plate the iron rod with nickel. Since reduction occurs here, this electrode is the cathode. Reduction always occurs at the cathode. If the other electrode does not release nickel ions into solution, the concentration of nickel ions in solution will decrease over time as they are reduced and plated onto the iron rod. The other electrode is the anode. Oxidation always occurs at the anode. Nickel atoms at the anode each lose 2 electrons and are oxidized to nickel 2+ ions, and the electrons lost travel up the wire. But is the anode pure nickel or not? If it is pure nickel, it releases only nickel 2+ ions into the electrolyte, and it will maintain the nickel ion concentration in solution, even though nickel ions are leaving solution as they plate onto the iron rod. So a pure nickel electrode is the best way to keep the process going. However, if the anode is a nickel alloy, it will release other metal ions into solution as well, and these will also be reduced at the cathode, resulting in both nickel metal and the other metal plating onto the iron rod together. So yes, the anode must be pure nickel. If we combine the two half equations, we get this redox equation. And since nickel 2+ ions are reduced and others are oxidized, we could simplify even further and write the equation in yellow as the net equation or the net reaction. Ultimately, nickel atoms from the anode end up being plated onto the cathode. In summary, we can see that iron is the negative electrode. The metal ions in solution do undergo reduction as they are plated onto the iron rod, and the anode is made of pure nickel. Since all three statements are true, the answer is D. Here we need to select the alcohol, the substance with a formyl group, and an unsaturated species. These are the compounds given to us. An alcohol must contain a hydroxyl group. The carbon to which the oxygen is attached must not be bonded to any other oxygens. Alcohols have the general formula CnH2n plus 2O. Compounds that have a formyl group are known as aldehydes. They have a carbonyl group near the end of the molecule, and to this is attached a hydrogen. An unsaturated compound refers to a hydrocarbon substance which contains at least one multiple bond between carbon atoms, that is, a double or triple carbon-carbon bond. Let's analyze each compound to find the alcohol, the formyl group, and the unsaturated molecule. If we analyze the structure for compound A, which is shown in full in the paper but slightly condensed here, we will notice it has this functional group at the end of the molecule. This is an aldehyde functional group or formyl group. So already we can deduce that compound A contains the formyl group. Then, looking at compound B, which is slightly condensed here, we will notice it contains halogens. This compound is a haloalkane, and since it contains alkyl branches, it is a branched haloalkane. For compound C, we are given a name, butanone. The suffix -one indicates we are dealing with a ketone. Butanone is a 4-carbon chain ketone. Ketones contain a carbonyl group, which is a carbon double bonded to an oxygen. Compound D shows the molecular formula of a compound, C4H10O. This formula has the form CnH2n plus 2O, where N is equal to 4. Since the molecular formula matches the general formula of an alcohol, compound D must be an alcohol. Note, however, that a class of compounds called ethers have the same general formula as alcohols. So the molecular formula for compound D could represent an ether. But if compound D is an alcohol, there are several possible structures we could draw. It all depends on the branching and on which carbon the hydroxyl group is. Here we have drawn just one of the possible structures. And this is the hydroxyl group. Then we are given the condensed formula for compound E. If we expand the condensed structure a bit, we will notice there is a carbon-carbon triple bond. And so this compound is an alkyne and is therefore unsaturated. Compound E is unsaturated. Let's finish by checking the other compounds to make sure we haven't missed anything. We are also given the condensed formula for compound F. Expanding this formula a bit, we will notice the COO functional group appears between two carbon atoms, which tells us this compound is an ester. Then the molecular formula is given for compound G, and it has 2 oxygen atoms. Possible functional groups which contain 2 oxygen atoms include carboxylic acids and esters. Compound H is shown in a condensed formula. This is its structure, and it contains only carbon and hydrogen with single bonds between all the carbons. So it is a saturated hydrocarbon. Specifically, it is a branched alkane. Finally, the alcohol is compound D, the formyl group is found in compound A, and compound E is unsaturated. The question asks us to give the IUPAC names of the 2 compounds. This is the structure of compound B. It is a branched haloalkane. And this is the condensed structure of compound E, which we can see after expanding it a bit is unsaturated. Since it has a carbon-carbon triple bond, it is an alkyne. Let's use the IUPAC rules for naming hydrocarbons and haloalkanes to name substance B first. First, find the longest carbon chain, and this gives the parent or root name. The longest chain must contain any double or triple bonds if they are present. This chain has only 5 carbons. This has 4, but this is the longest chain with 6 carbons. So the root name is hex. Then the suffix behind the root name or after the root name depends on saturation. Saturated compounds have names which end in -ane. Alkene names end in -ene, and alkyne names in -ine. This compound is fully saturated with only single bonds between carbons, and so we have hexane. Then the longest chain is numbered from the end closest to the double or triple bond. But if no multiple bond exists, we number from the end closest to a substituent, and we aim for the lowest numbers. We will not number the longest chain like this, as the bromines will then be on carbon 4. Instead, we number it like this, so that they are on carbon number 3. If a multiple bond exists, we would number it before the suffix name, but there are no multiple bonds in this compound. Then substituents are named before the parent name and are placed in alphabetical order. We have bromo substituents and methyl substituents, so we write bromo before methyl. The positions of the substituents are indicated, and since there is more than one of the same substituent, we need to indicate this before the substituent name. There are 2 bromines on carbon 3, and so we write 3,3 dibromo, and there are 2 methyl groups on carbon 4, so we write 4,4 dimethyl. So we have 3,3 dibromo, 4,4 dimethyl hexane as the name for substance B. Then for substance E, this is the longest chain and it has 5 carbons, so the root name is pent. Numbering from the end closest to the triple bond, as this takes preference over other substituents, we see that the triple bond is between carbon 2 and 3, and we use the lower of the 2 numbers in the name. So the suffix is 2-ine. There are 2 methyl groups on carbon number 4, and so we write 4,4 dimethyl in front of the parent name. There is one more rule on this list which we have not had to use here, and that is when more than one double or triple bond is present, we use prefixes before the suffix, diene, triene, etc. Finally, substance B is 3,3 dibromo, 4,4 dimethyl hexane, and substance E is 4,4 dimethyl pent-2-ine. Here we need to give a definition for functional isomers and identify 2 compounds which are functional isomers of each other. Functional isomers are compounds with the same molecular formula but different functional groups. So to identify the functional isomers, we must first write the molecular formula for each compound and then see which ones have the same molecular formula. Here are the molecular formulas. We can see that only these 2 compounds have the same molecular formula, C4H8O2, and they have different functional groups. One is a ketone, a compound with a carbonyl functional group, and the other is an aldehyde, a compound with a formyl functional group. So these 2 compounds are functional isomers. They are compounds A and C. This question asks us to identify the catalyst, the process which is occurring, the structure of substance F, and the name of a substance which we will call Z. This is compound F, and if we expand its condensed formula a bit, we get this structure. We can see that it has an ester group here. So compound F is an ester. Ester names have 2 parts. The first ends in -ile and the second in -ate. When naming an ester, the portion of the molecule attached to the ester oxygen is used for the first part of the name. Since there are 3 carbons, we write propyl. And the other portion of the molecule is used in the second part of the name. There are 2 carbons, and so we use the prefix eth for 2, and we get ethanoate. This ester is propyl ethanoate. We are told that it can be produced by the reaction of a carboxylic acid with another substance, which we will call Z. And we're told that a catalyst is used in this process. Now, esters are produced from the reaction between a carboxylic acid and an alcohol, and the byproduct is water. This type of reaction is called an esterification reaction. Now, which part of the ester comes from the alcohol and which from the acid? The first part of the name indicates the alcohol which was involved, which must be propanol, which is a 3-carbon alcohol, so compound Z is propanol. And the second part of the name tells us the acid which was involved. A 2-carbon carboxylic acid is ethanoic acid. A catalyst often used in esterification is sulfuric acid, H2SO4. This is a dehydrating acid. It removes an oxygen and a hydrogen from the acid and a hydrogen from the hydroxyl group of the alcohol, which produces water. Since this reaction involves the formation of water, it can also be called a condensation reaction. The acid carbon joins to the oxygen of the hydroxyl group of the alcohol to form the ester bond. Finally, the catalyst is sulfuric acid. The process is esterification. This is the structure of substance F, although it is partially condensed here and we have not shown the full structural formula. And the name of compound Z is propanol. The question asks us for a definition of vapor pressure and then the value of the vapor pressure for 2,2 dimethyl propane. We also have to give a reason for how we deduced the vapor pressure of this compound. We are given a table with 5 compound names, their molar masses, and the vapor pressure of 2 of the compounds. The missing vapor pressure values we have called X, Y, and Z, and these values are 58, 146, and 79 kilopascals. But we don't yet know which value belongs to X, which to Y, and which to Z. When a liquid is put in a closed system where particles cannot escape, some of the liquid particles evaporate, and some condense to reform the liquid. Over time, if the temperature is held constant, an equilibrium forms where the rate of evaporation is equal to the rate of condensation. The pressure of the gas or vapor in this equilibrium system is called the vapor pressure. So we can define vapor pressure as the pressure exerted by a gas which is at equilibrium with its liquid in a closed system at a fixed temperature. The vapor pressure of a substance at a certain temperature is dependent on how volatile it is, that is, how easily it evaporates, and its volatility depends on the strength of the intermolecular forces of attraction. So to find the vapor pressure of 2,2 dimethyl propane from the 3 given values, we must start by understanding and comparing the structures of compounds X, Y, and Z, so that we can then deduce the strength of their intermolecular forces. Pentane is a linear 5-carbon chain. Because pentane molecules are linear, they can get close together and have a high surface area in contact with each other, or we could say they have high surface interaction. This results in relatively strong van der Waals forces of attraction due to temporary dipoles. A relatively high amount of energy is required to overcome these forces to evaporate the liquid molecules, and therefore the vapor pressure which results is low. 2-methylbutane is slightly branched, resulting in less surface area interaction between molecules, as they can't get close to each other along their lengths. So the van der Waals forces are weaker than in pentane, and less energy is required to overcome these forces, making this compound more volatile than pentane. A higher volatility results in a higher vapor pressure. Then 2,2 dimethyl propane, which has the same molar mass as compounds X and Y, has even more branching and even less surface area interaction, as the molecule is very bulky. And so the van der Waals forces are even weaker than the previous 2 compounds. Even less energy is required to overcome these forces to evaporate these molecules, and so they are the most volatile compounds of X, Y, and Z, and produce an even higher vapor pressure than compounds X and Y. From this, we can assign the vapor pressures given. 58 kilopascals, the lowest value, belongs to pentane, 79 to 2-methylbutane, and the highest vapor pressure value, 146 kilopascals, belongs to 2,2 dimethyl propane. Finally, we will need to explain this deduction using the reasoning we have discussed. Here we have to figure out if butanol or propanoic acid have the lower boiling point and explain why their vapor pressures differ. This is the structure of butanol, which is an aldehyde. And this is the structure of propanoic acid, a carboxylic acid. The boiling point and the vapor pressure of a compound depend on the strength of its intermolecular forces of attraction. But the strength of intermolecular forces has an opposite effect on boiling point and vapor pressure. So let's draw in two molecules of each substance and investigate the intermolecular forces. The oxygen atom in butanol has a delta minus charge since it is highly electronegative, and the carbon atom to which it is bonded has a delta positive charge. The delta positive carbon on one molecule is attracted to the delta negative oxygen on an adjacent molecule. This force of attraction that is formed is a dipole-dipole attraction. Now there are also very weak London forces between these molecules, which arise from temporary dipoles. But the strongest intermolecular force in butanol is a dipole-dipole force. In propanoic acid, there are also dipole-dipole forces and London forces. However, these are not the strongest intermolecular forces. In propanoic acid, the hydroxyl oxygen has a slight negative charge, and the hydroxyl hydrogen a slight positive charge. These delta minus and delta plus charges are more pronounced or stronger than the charges on the carbonyl. A delta negative oxygen on one propanoic acid molecule is attracted to the delta positive hydrogen on an adjacent molecule. This force of attraction is a hydrogen bond, since the highly electronegative atom is bonded to a hydrogen specifically. Now dipole-dipole forces are weaker and hydrogen bonds are stronger. Little energy is required to overcome the weaker dipole-dipole forces during boiling, and so butanol has a lower boiling point. More energy is required to overcome the stronger hydrogen bond forces during boiling, and so propanoic acid molecules have a higher boiling point. For the first part of the question, we can conclude that butanol has the lower boiling point. Then we can see that the vapor pressure of propanoic acid is much lower than that of butanol, and we need to explain this. We have already seen that the strongest intermolecular forces in the aldehyde are dipole-dipole forces, which are relatively weak, while propanoic acid has strong hydrogen bonds. We also said more energy is required to overcome the forces between propanoic acid molecules. As a result, propanoic acid evaporates less readily and has a lower vapor pressure than butanol, which evaporates more readily. You would need to write a similar explanation in a short paragraph for the marks. We are given a flow diagram which shows reactions 1 to 5, and there are various questions to answer. First, we are asked what cracking means. In chemistry, cracking means a type of reaction which occurs under high temperature and pressure, where large hydrocarbon molecules are broken down into smaller, more useful ones, usually alkanes and alkenes. We're told that reaction 1 involves cracking, and we can see two products are formed. Since this product has the formula in the form CnH2n, we know we are dealing with an alkene. This is one possible structure for this compound, and it is called but2-ene. Since cracking usually produces an alkene and an alkane, the other product is most likely an alkane. Now reaction 2 shows an alkane producing a haloalkane, namely 1-bromobutane. Since a hydrogen is replaced by another atom, in this case bromine, this must be a substitution reaction. And since the haloalkane has 4 carbons, the alkane must also have 4 carbons, and is therefore butane. We are asked in the next question if the haloalkane is primary, secondary, or tertiary. These are the general structures of primary, secondary, and tertiary haloalkanes, where the R groups are alkyl groups, that is, carbon-hydrogen chains. The R groups may or may not be the same. Notice that in a primary haloalkane, the carbon to which the halogen is attached is bonded to only one other carbon in the alkyl R group, and this carbon is also bonded to two hydrogen atoms. In a secondary haloalkane, the carbon to which the halogen is bonded to two R groups and only one hydrogen. And in a tertiary haloalkane, the carbon to which the halogen is attached is not bonded to any hydrogens, but to three carbon atoms in the three alkyl groups. So the product of reaction 2 is a primary haloalkane, as we can see that the carbon to which the bromine is attached has one carbon attached and two hydrogens. Next, we need to give the full structure of this compound, which we have called compound B here. And we have already deduced its structure. It is butane. Next, we need to give the molecular formula of the initial compound which was cracked. We have called that compound compound A here. Since the two products produced from the cracking of compound A are both 4 carbon chain molecules, compound A must have 8 carbons. Now usually alkanes are cracked, and we will assume that the compound A is an alkane. The general formula of an alkane is CnH2n plus 2. Since N is 8, we can deduce that there must be 18 hydrogens. So the molecular formula is C8H18. Next, we need to give the inorganic substance which is needed in reaction 2. Since a hydrogen is replaced by a bromine atom, bromine is the inorganic reactant, Br2. We have already identified that this is a substitution reaction. The condition required for a substitution reaction of an alkane to occur is high energy, for example, from UV light. Here we are asked several questions that follow on from the previous video. Firstly, we must identify the specific type of elimination reaction occurring in the third reaction. In an elimination reaction, a small molecule is removed or eliminated. When a haloalkane undergoes an elimination reaction, a hydrogen atom and the halogen atom are removed. When a hydrogen and a halogen are removed, it is called a dehydrohalogenation elimination reaction. In this case, hydrogen bromide is removed. As a result of two atoms being eliminated with nothing to replace them, a carbon-carbon double bond is formed between the carbon atoms to which the two eliminated atoms were attached. This compound is but1-ene, an alkene. Next, we are asked to give an equation for reaction 4. The only information we have is that these two compounds, encircled in orange, are positional isomers. Positional isomers are compounds that have the same molecular formula. Both these compounds have 4 carbons and 8 hydrogens. The same functional group, they both have a carbon-carbon double bond, but the functional group or substituent is in a different position in the carbon chain. In but1-ene, the double bond is on carbon 1, and in but2-ene, it is on carbon 2. Following the arrow directions, we need to somehow move the double bond from carbon 1 to carbon 2 using the list of available reagents in the question paper. This means we will first need to open up this double bond in an addition reaction and then recreate a double bond in a new position, and this will involve elimination again. So let's look at this addition reaction first and the available reagents. What happens if we added hydrogen gas? The product would be butane. But there is no reagent available to remove 2 of the hydrogens selectively at carbon number 2 to form but2-ene, so we can eliminate hydrogen. If we added bromine, we would get 1,2-dibromobutane. And if we used concentrated sodium hydroxide, this would remove a hydrogen and a bromine. Then in the elimination reaction, a haloalkene would be left, bromobutene, and not an alkene. So bromine is not suitable. We can eliminate it as a reagent. If we added hydrogen bromide to the alkene, the hydrogen atom would add on to one of the carbons at the double bond, and the bromine atom would add on to the other carbon. It is more likely for bromine to add on to carbon number 2, according to Markovnikov's rule, but it could instead add on to carbon number 1. Then, if we used concentrated sodium hydroxide, we would induce a dehydrohalogenation elimination reaction, where a hydrogen and a bromine are lost, and a double bond is formed, either on carbon 1 or on carbon 2. So hydrogen bromide is a suitable reagent for the addition reaction. The full structural equation for the addition reaction will look like this, where bromine is added onto carbon 2, or like this, where bromine is added onto carbon 1. We are then asked for the equation for elimination, and there are two possible answers you can give. One, which produces a double bond on carbon 2, and the other which produces a double bond on carbon 1. Finally, we need the IUPAC name of this alkene. It can be but2-ene as drawn here, or but1-ene. The root name or parent name but tells us there are 4 carbons in the chain. The suffix -ene tells us there is a carbon-carbon double bond, and the number before the suffix tells us the lower number of the 2 carbons that the double bond is between. This question asks us what reaction rate means, and then we have to use the given graph to work out the mass of aluminium remaining after 5 minutes has passed. The rate of a reaction is a measure of how the quantity of either a reactant or a product changes over time. The numerator can be the change in mass or concentration or moles or volume. For example, if it's the rate in terms of volume change over time, it would be the final volume minus the initial volume over the final time minus the initial time. For the given reaction, where a piece of aluminium is placed into excess hydrochloric acid, hydrogen gas is produced, and the volume of the gas can be measured over time and plotted on a graph. Initially, the volume of gas produced increases rapidly, as we can see from the steep gradient. Then its rate of production begins to slow down, and eventually it is no longer produced when the reaction is over. The gradient of the graph at any point in time tells us the rate at that point in time, but we can take the gradient using 2 points on the graph if we want to find the average rate over a certain period of time. We are told that the average rate for the first 5 minutes is 0.033 decimeters cubed per minute. And we need to determine the mass of aluminium left at 5 minutes. How can we do this? Well, since we know the rate and the corresponding time period, we can calculate the volume of hydrogen gas produced, which is handy as there are no values for the volume of hydrogen on the y-axis of the graph. We can then use this volume and divide it by the given molar gas volume to calculate the moles of hydrogen gas produced under these conditions. Then, using the balanced equation, we can work from the moles of hydrogen to a moles of aluminium. And then we can determine the mass of aluminium, since we can work out its molar mass. So let's do that. We can take the rate equation, put in the given average rate for the first 5 minutes, and the change in time, and we can calculate a volume of hydrogen produced in 5 minutes, which is 0.165 decimeters cubed. Taking this value and dividing by the given molar volume, which is the volume occupied by 1 mole of a gas at a specific temperature and pressure, we get 6.74 times 10 to the minus 3 moles of hydrogen produced at 5 minutes. Now, since 2 moles of aluminium produces 3 moles of hydrogen, according to the stoichiometry in the balanced equation, we can work out the corresponding moles of aluminium that would be used up to produce the moles of hydrogen we just calculated. We have not shown how to do this calculation here, but one way is to cross-multiply and solve for x. Solving for x, we get 4.49 times 10 to the minus 3 moles of aluminium reacted or used up in 5 minutes. We can then convert the moles of aluminium reacted to a mass by multiplying the moles by its molar mass. We get 0.12 grams of aluminium used up in 5 minutes. But the question wants the mass of unreacted or remaining aluminium at 5 minutes. This is calculated by taking the starting mass minus the mass which was used up in the reaction. The starting mass was given to us. It is 0.5 grams. So taking 0.5 grams minus the 0.12 grams used up, we get 0.38 grams of aluminium remaining. Next, we need to explain why the rate changes in the first 5 minutes and isn't a constant value. Well, as time passes, so more aluminium is used up, and its mass and surface area decrease. This means fewer aluminium atoms are exposed to acid molecules in solution. And so there are fewer effective collisions per second. And so the rate slows down. Here we will discuss 2 questions for 2 further experiments, namely what changes happen on the graph and how do gas volumes compare. For the first of the 2 questions, we know the mass of aluminium is the same in both experiments 1 and 2. But we are told the concentration of the acid is doubled to 2 moles per decimeter cubed. This graph in orange is the one that was given to us for the first experiment, and we need to draw the graph for the second experiment. The steepness of the graph indicates the rate of production of hydrogen and the rate of the reaction. Now we know that the rate of a reaction is influenced by the concentration of solutions, the pressure of gases, temperature, the surface area of solids, and whether a catalyst is present or not. In experiments 1 and 2, the concentration of the acid differs, and so this will affect the rate of the reaction and how quickly hydrogen is produced. In the first experiment, the concentration of acid is lower. This will result in fewer effective collisions per second between the aluminium and the acid particles, and therefore the rate of the reaction is slower. While in the second experiment, the concentration of acid is higher, which will result in more effective collisions per second between reactant particles. And so the rate is faster. We said that the steepness of the volume time graph indicates how fast the hydrogen is produced and indicates the speed of the reaction. So since the rate of the second experiment is higher than the rate of the first experiment, the graph for experiment 2 will have a steeper gradient for the duration of the reaction. Now, it is the amount of limiting reagent which determines the amount of product that can form. In both experiments, there is the same amount of limiting reagent. And so both experiments will produce the same amount of hydrogen gas, just at different rates. And this can be shown on the graph by the same volume of hydrogen at the maximum point. Then we have to see how the volumes of hydrogen produced in the first and third experiments compare. We are told the same mass of aluminium is used in each, but that a strip of metal is used in the first, while powdered metal is used in the second. We said earlier that the surface area of solid reactants affect the reaction rate. Compared to powdered metal of the same mass, a strip has lower surface area as there is just one big particle, which means there are fewer aluminium atoms exposed to hydrochloric acid, and so the frequency of effective collisions is lower. And therefore, the rate is lower or slower. However, for powdered metal of the same mass, there is a much higher surface area as there are many small particles. As a result, the frequency of effective collisions is higher. and so the reaction rate is faster. So we know the rate of experiment 3 is much faster than the rate of experiment 1. But how do the volumes of the gas product compare? Again, it is the amount of limiting reactant which determines the amount of product that can form. And we have the same amount of limiting reactant in both experiments 1 and 2. And so the same amount of gas will be produced in each experiment, and the volume of gas produced will be the same. The only difference is that this gas is produced at different rates. This question asks what was altered in the system to generate the second curve, and we need to explain why. We have two Maxwell-Boltzmann curves. A Maxwell-Boltzmann curve shows how kinetic energy is distributed amongst particles in a system. Looking at graph 1, we can see that the bulk of the area under the peak shows that a large proportion of the particles in the system, or we could say most of the particles, have a relatively low kinetic energy, and only a small proportion of the particles have very high kinetic energy. The same is true even when the graph is shifted to the right, as is the case with the second curve. Again, most particles have a relatively low kinetic energy, and only a small proportion have high kinetic energy. So what changed in the system to move the curve from position 1 to position 2? We can see that the second curve is shifted to higher kinetic energies and is slightly flattened. So graph 2 represents the system with higher kinetic energies, and it will therefore also have a higher average kinetic energy. Now, average kinetic energy is proportional to temperature. In fact, temperature is a measure of the average kinetic energy of particles in a system. So since the average kinetic energy increases from graph 1 to graph 2, temperature increases too. We can deduce that graph 1 represents a lower initial temperature and graph 2 represents a higher final temperature. So the change is that temperature was increased. The explanation is that the second curve is shifted to the right and a larger fraction of particles have higher kinetic energy. This question has several subparts, all to do with a gaseous equilibrium occurring in a closed system. A closed system is one where matter cannot enter or escape because the vessel is sealed, but energy can move to and from the system. This is the reaction at equilibrium. First, we need to give a definition for the phrase chemical equilibrium. A chemical equilibrium is a state in a reversible reaction where the rates of the forward and reverse reactions are equal. The graph shows how the concentrations of the three species at equilibrium in the reaction change when certain reaction conditions are altered. Now, Le Chatelier's principle governs and explains what happens to an equilibrium when a condition is changed. It says that if a chemical system that is at equilibrium experiences a change in concentration, temperature, or pressure, the equilibrium will shift in the direction that reduces the effect of that change, and a new equilibrium will be established. So we are told that oxygen gas is added to the vessel. We need to identify which species, 1, 2, or 3, represents the oxygen reactant. So we need to look at what is happening here on the graph. Notice that when oxygen gas is added, reactant 1 immediately increases in concentration, and we can see this from the short vertical line. Since oxygen was added, and this species concentration immediately goes up, this species, species 1, must be oxygen. So oxygen gas is represented by 1. The next change which occurs is a change in volume of the container. Did the volume increase or decrease? Notice that when this change occurred, the concentrations of all three species immediately decreased. This tells us that the volume of the vessel was increased. Now we are asked for the corresponding pressure change. An increase in gas volume corresponds with a decrease in gas pressure. And we can give this explanation we just discussed for the next question. Next, we need to identify compound 3. One way to do this is to look at what happens to the concentrations of the 3 substances when oxygen is added. We said that when oxygen is added, the concentration of substance 1, which is oxygen, increases immediately. And then it starts to decrease, which means it is being used up. Notice that at the same time, the concentration of substance 3 decreases too. Since oxygen gas is a reactant, then substance 3 must also be a reactant, namely carbon monoxide. And at the same time, the concentration of substance 2 increases, so it must be the product carbon dioxide, whose concentration goes up as the reactants combine together to form it in the forward reaction. We can use the explanation we just discussed for the next question, or we could explain it using Le Chatelier's principle in more depth. We would then say, when more oxygen is added, the equilibrium will shift to the right to decrease the concentration of oxygen, and so the forward reaction is favored. And this will cause the concentrations of the 2 reactants to decrease, and the concentration of the product to increase. The next change which occurs is a temperature change. We need to identify if the temperature went up or down. If we have a look at the reaction given to us, we can see that the enthalpy change is negative, and so the forward reaction must be exothermic. And therefore the reverse reaction must be endothermic. Exothermic reactions are energy releasing and so are favored by cooling, while endothermic reactions are energy absorbing and so are favored by heating. We can see that the concentration of oxygen gas starts to decrease when the temperature is changed. And so does the concentration of carbon monoxide, while the concentration of carbon dioxide increases. This tells us that the forward reaction is being favored by the temperature change, and that the equilibrium is shifting to the right. If the forward reaction is favored, the system must be being cooled, and so the temperature has decreased. This explanation we just discussed will help us answer the last question. This question asks us to determine how much carbon monoxide is left at equilibrium, and we will use grams since we're talking about mass. We are given this reaction equation at equilibrium, and we're told the volume of the vessel and that the equilibrium constant is 4 at the particular temperature this reaction is occurring at. We are also given the initial number of moles of each species before equilibrium is established. Since we want the amount of carbon monoxide present at equilibrium, we can use an ICE table. Some call it a rice table, where R is the reaction with a ratio, in this case 1:1:1:1. I is the initial moles of each species. C is the changed moles, which is the moles of reactants used up and the moles of products formed. And E is the moles left at equilibrium. Now we do not know how many moles of reactants are used up or how many moles of products form at this particular temperature. But we can express their values in terms of X. And since the mole ratio is 1:1:1:1, then if X moles of carbon monoxide are used up, X moles of water are also used up, and X moles of hydrogen will form, and X moles of carbon dioxide will form. Remember, the changed moles must be in the same ratio as the stoichiometric coefficient ratio. To get the equilibrium moles for the reactants, we take the initial moles minus how much was used up. And so we get 0.6 minus X moles of each reactant present at equilibrium. Then, to get the equilibrium moles for the products, we take the initial moles plus how much was formed. And so we get 0.1 plus X moles for each product present at equilibrium. Now these mole values are in terms of X. We need to be able to solve for X so that we can work out an actual mole value for carbon monoxide, and then from this we can work out a mass of carbon monoxide. We can use the equilibrium constant expression to help us solve for X. Remember that an equilibrium constant expression is the concentrations of the products divided by the concentrations of the reactants, with each raised to the power of its stoichiometric coefficient, which is 1 for each in this case. Now we know that the value of Kc is 4, and we need the concentrations of the 4 species for this equation, but we only have the moles of each species in terms of X. However, we know that concentration is equal to number of moles divided by volume. So if we take the number of moles of each species in terms of X and divide by the vessel volume of 2 decimeters cubed, we get the concentration of each species at equilibrium in terms of X. We can now substitute these equilibrium concentrations into the equilibrium constant expression, as well as the value for Kc. The 2's in the denominators will cancel, and we can take the square root of each side. Then, getting rid of the denominator and multiplying out the bracket, we can solve for X, which is 0.367. Now, since the moles of carbon monoxide at equilibrium is 0.6 minus X, we can substitute in the value of X, and we get 0.233 moles of carbon monoxide present at equilibrium. All that is left to do is to convert this to a mass. We know that number of moles is equal to mass divided by molar mass, and so the mass of carbon monoxide is its moles times its molar mass. Putting in the mole value we just calculated and the molar mass of carbon monoxide, we get 6.52 grams at equilibrium. The first part of this question asks us to explain what a weak base refers to. Bases tend to generate hydroxide ions in aqueous solution. Strong bases generally dissociate or break apart into ions and generate hydroxide ions, while weak bases generally react with water and produce hydroxide ions. The important difference is that for equal concentrations of a strong base and a weak base, the strong base will dissociate completely and generate a high concentration of hydroxide ions, while a weak base dissociates or ionizes only partially, forming an equilibrium, and generates a low concentration of hydroxide ions. So strength refers to the degree of ionization, and again we would have to compare equal concentrations of a strong base and a weak base, and we can see the concentrations of ions produced differs. It is worth committing to memory the formulas and names of the common strong acids and bases, and the common weak acids and bases. Next, we have to take the carbonate ion, which is found in the weak base potassium carbonate, and we are asked to find its conjugate acid formula. According to Bronsted-Lowry acid-base theory, an acid is a proton donor and a base a proton acceptor. So the acid donates or gives a proton, which is a hydrogen ion, to the base. And these are the general formulas of the products. The conjugate acid product differs from the base by 1 proton, and the conjugate base product differs from the acid by a proton. These two are a conjugate acid-base pair, and these two are a conjugate acid-base pair. So the carbonate ion, which is a base, must accept a proton to form its conjugate acid. The conjugate acid of the carbonate ion will differ from the carbonate ion by a proton. So the conjugate acid of the carbonate ion is HCO3-, which is called hydrogen carbonate. Since the carbonate ion had a 2- charge, when it gains a positive proton or a positive hydrogen ion, it ends up with a 1- charge. This question asks us to find what the value of X and Y are in the table and to give a reason for the choice of methyl orange as an indicator. We are given the reaction equation. We can see we have an acid. Specifically, hydrochloric acid is a strong acid, which means it dissociates fully in solution. And we are told potassium carbonate is a weak base. We saw in the previous video that weak bases dissociate only partially in solution. Now this weak base is a metal carbonate. When an acid and a metal carbonate react, a salt, in this case potassium chloride, water and carbon dioxide are produced. This is a type of neutralization reaction, and we are told a titration experiment is performed with the acid and base. 25 centimeters cubed of the acid are used, and this would have been pipetted into the conical flask. We are also given its concentration. The burette would have had the potassium carbonate solution in it, and we don't know its concentration. We are given a table showing the readings on the burette in 2 trials or runs, which are repetitions of the titration. We need to start by calculating X. In trial 1, the initial reading is 6.5 centimeters cubed, which is read off the bottom of the meniscus. We do not know the final reading, but we are given the volume of the potassium carbonate solution used or transferred from the burette into the acid in the flask. The volume transferred from the burette is called the titer. The titer is 20.05 centimeters cubed. So how do we work out X? The titer volume is equal to the difference in the 2 readings, namely the final reading minus the initial reading. So if we rearrange this formula, we get final reading is equal to titer minus initial reading. Putting in the values, we get 26.55 centimeters cubed for X. Then we are asked for the value of Y. Again, the titer or volume transferred is the difference in the final and initial readings. So the initial reading is the final reading minus the titer. The initial reading is Y. The final reading is 48.3 centimeters cubed, and the titer is 20.15 centimeters cubed. Putting in the values and solving, we get 28.15 centimeters cubed. We are then asked why methyl orange is chosen as an indicator. First, we need to know what equivalence point is. It is the point in a titration at which all the acid and base are used up. An indicator changes color just after equivalence point, at the end point, and the color change tells us the reaction is over. Different indicators change color in different pH ranges. We need to figure out the pH range in which methyl orange changes color. A strong base and a strong acid react to produce a neutral solution with pH about 7 at equivalence point. A strong acid and a weak base at equivalence point produce a slightly acidic solution. A weak acid and a strong base produce a slightly basic solution. For a weak acid and a weak base, the pH at equivalence point depends on the relative strengths of the acid and the base. In the given reaction, we have a strong acid and a weak base reacting, so the final solution at equivalence point will be slightly acidic. So methyl orange must change color in the slightly acidic region. The question asks us to determine the concentration of the potassium carbonate solution. To calculate the concentration of the solution, we can first use the data given to us, that is the concentration and volume of the acid, and use these to calculate the moles of acid that react. And then, from the moles of acid, we can find the moles of potassium carbonate that react. And then we can find the concentration of the potassium carbonate solution using its moles and its volume, which is the average titer. So we can start by taking the concentration times the volume of the acid, and we get 0.0025 moles of acid reacted. From the balanced equation stoichiometry, we can see that for every 2 moles of acid reacting, 1 mole of potassium carbonate reacts. And since 0.0025 moles of the acid reacts, we know that X, which is the moles of potassium carbonate that reacts, will be half. Solving for X, we get 0.00125 moles of potassium carbonate that reacts. All that is left to do is to use the moles of potassium carbonate and divide by the volume of the potassium carbonate solution to get its concentration. We know the mole value, we just calculated it. And the volume value is the average titer. Since there are 2 titer values, we can add them and divide by 2 to get the average titer, which is 20.1 centimeters cubed. And we must convert this to a value in decimeters cubed by dividing by 1000. So the average titer in decimeters cubed is 0.0201 decimeters cubed. Putting this value into the denominator and then solving, we get 0.0622 moles per decimeter cubed for the concentration of potassium carbonate. We are required in this problem to determine the value of the coefficient in front of water in the given formula. This is the formula of a hydrated potassium carbonate salt. We do not know what the value of N is, but we know it must be a whole number, 1, 2, 3, etc. It cannot be a fraction. We know the mass of the entire salt weighed out to make the titration solution. It is 6.525 grams. And this mass includes the mass of potassium carbonate as well as the waters of crystallization. We know the concentration of the solution that was prepared from this mass. We calculated it in a previous question. And we are told the volume of the solution. Now to solve this problem, we need to know the molar mass of the hydrated salt, which is made up of the molar mass of 2 potassiums, 1 carbon, 3 oxygens, and N waters, where there are 2 hydrogens and 1 oxygen atom per water molecule. And since we know the individual molar masses of each element from the periodic table, we can generate a formula which will allow us to solve for N if we know capital M, the molar mass. So let's start by determining the molar mass of the whole salt. We can take the concentration and volume of the solution to find the moles of potassium carbonate, which is 0.0373 moles. Using the mass that was dissolved, which is equivalent to this number of moles, we can get the molar mass of the compound, which is 174.93 grams per mole. Substituting this molar mass into the molar mass formula of the compound, we can move all the terms to the left except the term containing N, simplify, and get N by itself. Finally, N is equal to 2. We are asked to discuss how we know this is a redox reaction using oxidation numbers. This is the reaction occurring. Oxidation number or oxidation state is a theoretical charge we can assign to an atom in a compound if all the bonds in the compound were treated as ionic bonds. It is a way to model or understand how charge is distributed in a compound, and it helps us determine which species is oxidized and which is reduced in a redox reaction. In a redox reaction, the oxidation numbers of 2 elements change, so we must first assign oxidation numbers to each element in this reaction, and then investigate how they change to prove that this is a redox reaction. Let's look at the rules used to assign oxidation numbers. Firstly, an element, whether it is monatomic or diatomic, etc., has a 0 oxidation number. Solid magnesium is an element and so has 0 for its oxidation number. And diatomic hydrogen is also an element, and so it also has 0 for the oxidation number. Monatomic ions have an oxidation number equal to their charge. Then atoms in a compound, whether the compound is covalent or ionic, have the following oxidation numbers. +1 for the group 1 elements. So hydrogen in hydrochloric acid is +1. Group 2 elements have a +2 oxidation number. So magnesium in magnesium chloride is +2. Group 3 elements are +3. Group 14 elements can be +2 or +4. Group 15 elements have different oxidation numbers, but we have no group 15 elements here. Oxygen in group 16 always has -2 as its oxidation number, except in peroxides. Sulfur can have different oxidation numbers. Group 17 elements have a -1 oxidation number, and so chlorine in hydrochloric acid is -1, and each chlorine in magnesium chloride is -1, so we can write its oxidation number underneath. But there are 2 chlorine atoms in magnesium chloride, and so together they contribute -2, and we can write this above. Transition metals have variable oxidation states. Then, oxidation numbers must add up to 0 in a neutral compound. So the 2 compounds in the reaction have oxidation numbers adding up to 0. The last rule is that in a polyatomic ion, the oxidation numbers add up to the charge on the ion, but we have no polyatomic ions here. Now, we have assigned oxidation numbers to each element in this reaction, and we must look at how the oxidation numbers change. Notice that each chlorine still has an oxidation number of -1 even after the reaction. The oxidation number of chlorine has not changed. However, the oxidation number of hydrogen has changed from +1 to 0. Each hydrogen gained an electron, and so hydrogen is reduced. The oxidation number of magnesium has changed from 0 to +2. Magnesium lost electrons, so magnesium is oxidized. Giving the oxidation numbers before and after the reaction for those elements where the oxidation number changed proves that this is a redox reaction. Here we need to identify the oxidizing agent. In the previous question, we deduced that hydrogen is reduced and magnesium is oxidized. An oxidizing agent is the species in a reaction which causes the oxidation of another species by taking electrons from it. So oxidizing agents are themselves reduced. Hydrochloric acid causes magnesium to be oxidized and takes electrons from magnesium. In the process, hydrochloric acid is reduced. Hydrochloric acid is the oxidizing agent. A reducing agent is the species in a reaction which causes the reduction of another species by giving electrons to it. So reducing agents are themselves oxidized. Magnesium causes hydrochloric acid to be reduced by giving electrons to it, and in the process, magnesium is oxidized. Magnesium is the reducing agent. Finally, the oxidizing agent is hydrochloric acid. The question asks about 2 acids and their reaction with copper. We are asked why dilute hydrochloric acid and copper do not react, and whether dilute nitric acid and copper will react or not, and we need to explain each answer in terms of oxidizing or reducing agent strength. The table of reduction potentials lists many reduction half reactions from left to right, and their reduction potentials. Here we have shown just 3 half reactions needed for the 2 questions in this video. Reduction potential is the measure of the tendency of an electrode to gain electrons and undergo reduction. The more positive the reduction potential, the more likely the species is to be reduced and gain electrons. And the less positive the value, the more likely that element is to be oxidized. In other words, if we take 2 reactions, the one with the more positive electrode potential is more likely to go in this direction, which is reduction, compared to a reaction below it, which is more likely to go in this direction, which is oxidation. So species to the top left are stronger oxidizing agents than the bottom left, as they are more likely to undergo reduction and gain electrons from another species, and thereby oxidize the other species. And species to the bottom right have a greater tendency to lose electrons and be oxidized, and thereby reduce another species. we can say an element which is a stronger reducing agent will reduce an element that is a weaker reducing agent. So, when dilute hydrochloric acid, which contains hydrogen ions, and copper are put together, no reaction will occur. This is because copper is a weaker reducing agent than hydrogen, and so cannot reduce hydrogen ions to hydrogen gas. And when nitric acid, which contains nitrate ions, is mixed with copper metal, because the nitrate ions are a stronger oxidizing agent than the copper 2+ ions, the nitrate ions in the acid will oxidize copper metal to copper ions. So yes, a reaction does occur with nitric acid and copper. This question asks us to determine the net ionic equation and how a different reducing agent influences the EMF. We are told the cell is a galvanic cell. In a galvanic cell, a spontaneous redox reaction occurs, and this generates electrical current in the wire. A galvanic cell always has two half cells, which are usually separated by a salt bridge. We are given the cell notation here. In cell notation, the double line represents the salt bridge, and on either side is information about the two half cells. The information written to the left of the double line is the information for the anode and the anode electrolyte. The information to the right is for the cathode electrolyte and the cathode. So on our diagram, we can label the anode as lead. Its electrolyte contains lead 2+ ions. The cathode is platinum, and its electrolyte is a mixture of iron 2+ ions and iron 3+ ions. Oxidation occurs at the anode and reduction at the cathode. During oxidation, the lead metal of the anode loses electrons to the wire, and these travel to the cathode. At the same time, the lead electrode loses lead 2+ ions into the solution. Specifically, 2 electrons are lost for every lead 2+ ion which goes into solution, and so this is the oxidation half reaction. During reduction, iron 3+ ions each gain an electron from the cathode and form iron 2+ ions in solution. So no plating or deposition of iron occurs onto the cathode. Rather, the platinum electrode merely supplies electrons to the ions in solution, reducing them from 3+ ions to 2+ ions. This is the reduction half equation. Now that we have the oxidation and reduction half equations, we can add them to get the overall redox equation. We need to cancel electrons, so we must multiply the reduction half equation by 2. Now the electrons on the left and the right can cancel since there are 2 electrons on each side. We can add what remains, and we get solid lead metal reacts with 2 iron 3+ ions to produce lead 2+ ions and 2 iron 2+ ions. This equation is balanced. The charges are balanced too. This is the net ionic equation. A net ionic equation shows only the chemical species actually involved in the reaction and which undergo a change. It does not include spectator ions. We do not know what the negatively charged spectator ions are here. Next, we are told a stronger reducing agent is used, and we need the effect on the EMF. Now the species which is oxidized is the reducing agent. So here the reducing agent is lead. And the difference in the electrode potentials of the two half cells will give a voltage reading on the voltmeter. The initial EMF is the voltage or potential difference before the reaction starts, when no current is flowing, when the circuit is open. And at this point, this voltage is at its highest, and it decreases over time when the reaction starts. The formula for the EMF is the cell potential is equal to the electrode potential of the cathode minus the electrode potential of the anode. If a stronger reducing agent is used, the electrode potential value for the cathode will be larger. This will result in a larger E cell In other words, a larger EMF. So the effect of a stronger reducing agent on the EMF is that the EMF increases. We are given a reaction equation and are asked to deduce whether the reaction is spontaneous or not. We are told solid silver metal is placed in a lead 2 nitrate solution. And this is the reaction equation which we have to figure out is occurring spontaneously or not. To determine if the reaction is spontaneous or not, we need to know the cell potential, E cell. Cell potential, also called cell voltage, is the potential difference between two half cells and is measured in volts. Now, we do not have two half cells here, but we can still use the cell potential to determine the spontaneity of a reaction if we know the oxidation and reduction half equations. A positive cell potential indicates a spontaneous reaction, and a negative value a non-spontaneous reaction. A non-spontaneous reaction would require the input of external energy to drive the reaction. We can find the equation for cell potential in the data sheets. It is E cell is equal to the electrode potential of the cathode minus the electrode potential of the anode. Or we can say the electrode potential for the reduction process minus the electrode potential of the oxidation process. Since we have no cathode or anode here, let's remove the top equation. We need to figure out the oxidation half reaction and the reduction half reaction. Then we must look up their electrode potentials on the table of electrode potentials. We start by filling in oxidation numbers, and silver has a value of 0 since it is an element. The same goes for lead. The oxidation number of monatomic ions is the same as their charge. So therefore 2 plus ions have a 2 plus oxidation number and 1 plus ions a plus 1 oxidation number. Silver's oxidation state is changing from 0 to plus 1. Silver is losing electrons and so it is oxidized. We can find this oxidation half reaction on the table of electrode potentials. Now this equation written from left to right is a reduction, but remember we are looking at the reverse half reaction, which is an oxidation. The electrode potential value for the forward reaction, which is written as a reduction, is positive 0.80 volts. This value will be converted to a negative value when we substitute it into the cell potential equation, since we are looking at the reverse half reaction, the oxidation half reaction. Then lead 2 plus ions each gain 2 electrons and are reduced to lead metal. This is the half equation which we must look up on the table of electrode potentials. The equation as written from left to right is a reduction, and its associated electrode potential is negative 0.13 volts. We can put these values into the cell potential equation, and we get negative 0.93 volts. The negative sign tells us that the reaction given to us is non-spontaneous. To get the reaction to occur, external energy would need to be used to drive the reaction. This question gives us an electrolytic cell, and we need to answer a series of questions related to it. An electrolytic cell is a type of electrochemical cell in which electrical energy is supplied by a power source to drive a non-spontaneous redox reaction. This can result in the decomposition of an ionic substance into its elements, or the formation of new substances from water if the solution is aqueous at the electrodes. Firstly, we need to define the term electrolyte. An electrolyte is a substance or solution that contains mobile ions and so can conduct electricity. Here we have an electrolyte solution instead of a molten electrolyte, and the species in solution are positive sodium ions, negative chloride ions, and water molecules. So the concentrated sodium chloride solution is the electrolyte, as it contains dissolved sodium ions and chloride ions, which are free to move about, and so when a current is applied to the ions, which are charge carriers, they can move and complete the flow of charge in the circuit. Next, we need to write down the main oxidation half reaction occurring. The positive terminal of the cell is attached to the positive electrode, and the negative terminal to the negative electrode. Negatively charged chloride ions in solution are attracted to the positive electrode. They each donate an electron to this electrode and get oxidized. Oxidation occurs at the anode. The electrons lost by chlorine travel up the wire to the other electrode. This is the oxidation half reaction occurring at the anode. We can see that 2 chloride ions are needed to form 1 chlorine gas molecule. This is the main oxidation half reaction occurring. Now, water itself can also be oxidized. However, since the solution is concentrated, there are a lot of chloride ions in solution, and they therefore get oxidized instead of water. If the solution was dilute sodium chloride, then there would be a low concentration of chloride ions, and water would be preferentially oxidized. Further explanation than this is not required at school level. An easy rule to remember is that concentrated chloride solutions are oxidized to chlorine gas, and dilute chloride solutions have water being oxidized instead to oxygen gas. We also need to give the products formed at electrode 2. Electrode 2 is the cathode. Reduction occurs at the cathode. The possible species that could be reduced are sodium ions or water. To decide which one is preferentially reduced, we need to compare their reduction potentials. In other words, the ease with which they are reduced. Looking on the table of reduction potentials, we can see that the reduction of sodium has a potential of negative 2.71 volts, and the reduction of water has a potential of negative 0.83 volts. Water has a less negative reduction potential value than sodium ions. So water is much easier to reduce. So even though sodium ions are present, water is reduced instead of sodium ions. We can see from this half reaction that the products of the reduction of water are hydrogen gas and hydroxide ions. Finally, we need to explain why we get the formation of hydrogen and hydroxide ions at the cathode instead of the reduction of sodium ions to sodium metal in terms of the strength of oxidizing agents. Remember, an oxidizing agent is itself reduced. Although both sodium ions and water could act as oxidizing agents and be reduced, the species that is actually reduced is the stronger oxidizing agent. We can say a stronger oxidizing agent gains electrons more easily, and so is reduced instead of a weaker oxidizing agent. Since water is the stronger oxidizing agent, water is reduced.